C'est bon? Bon, j'y vais ou... Ouais. Okay, good afternoon, everybody. Welcome back. So my name is Antoine Levitt. I work in the mathematics lab in Orsay. And I'm going to talk about numerical optimization. So basically, the numerical counterpart of what Eric did. The numerical methods used for optimization and how they work and why they work and how they don't work and so on. So I'm going to start with basic unconstrained optimization, and then I'm going to move on to constrained optimization, in particular using the geometrical framework that Eric began to talk about. Okay. Please feel free to interrupt me at any time if there are questions. So, optimization, I'm going to talk about the same problem as Eric did. And at the beginning, I'm going to talk about this. Okay, so simple, unconstrained optimization. So the first thing I'm going to say is that I'm only going to consider problems like this, so continuous optimization. So discrete optimization is something else completely. It works with very different methods, and I don't know at all how it works, so don't ask me. So here we're going to optimize with respect to continuous variables. Okay. The second thing is we're going to talk about local optimization. So I'm not going to be interested in finding the global minimum of this guy, because in general, that's a very, very hard problem. I'm just going to be looking for local minima. So if you have a function that looks, I don't know, like this is the global minimum. But if you start here, my goal is to find that, not that point. Okay. If you want to find the global minimum, then you have to look at global optimization. And global optimization is very, 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 very hard problem because it's completely global, right? You have to, in principle, explore the whole space. So if you don't have additional structure or additional information on your objective function, this is intractable in practice. The best we can hope is local minimization. And maybe if you're feeling very fancy, you take a few points. You start a local minimization at all your few points. You take the best. Okay. Sorry, that's life. Okay. So to do that, I hope all of you know this guy, which is going to be kind of the star. Everybody knows this, right? This is the gradient methods. So we are going to look at methods like this. Typically, when you do optimization, you have three kinds of methods: zero order, first order, and second order. This is the first order method, meaning it uses information on the first derivatives, on the gradients. You also have second order methods. And the simplest one is this. This one. Okay, this is Newton method. So this is not equal to this. This is gradient method, gradient descent, steepest descent, and this is Newton. Okay, so this is first order, this is second order. Second order just because it uses Hessian information. Zeroth order methods, I'm not going to talk about much because zeroth order methods are not very practical and if you are in high dimension. So if you have like 5 parameters, maybe you can try zeroth order optimization. But as soon as you go to a large number of parameters, you have to use gradient type information. Yes.
Just out of curiosity, the zeroth order methods are like simplex?
Yes, typically like this. So you explore your state space. It's some kind of it's some kind of refinement. You take a few points, then you do some kind of bisection. It's a generalization. The problem is that these scale very, very badly with the dimension because you have to keep track of the whole geometry of a simplex or like a hypercube or something. And this is very intensive in high dimensions. So you need gradients. So the first step in tackling any optimization problem is computing the gradients. This is very often nasty, but it's something that has to be done because otherwise you're in very bad shape for first understanding your problem, because you have, if you want to understand the optimality condition, this is equal to 0. And second, doing any kind of good numerical methods. Fortunately, computing gradients is in principle not too expensive. So this is a very surprising statement if it's the first time you hear it. If you have a function that takes like 1 second to compute in dimension 10,000, then the gradient in principle takes 1 second to compute. Okay, so okay, maybe it's I'm the first one to be I'm the only one to be surprised, but I find it surprising. So you can always compute a gradient using a better algorithm than finite differences, say. If you're doing finite differences, you have to do n calls to your function. This is a very bad way of doing it. And what you should use is a joint method or fancy methods. So there are plenty of tricks in practice. So if the function is simple, you just compute by hand the gradient, you find it, you code it. But if not, you use some kind of adjoint method for reverse mode automatic differentiation, techniques like this. And these compute the gradients of a function, no matter how complicated, in asymptotically the same time as it took to call the function once. Okay, and this is based on versions of the chain rule. So if you have a function x, y, f, okay, so given x, you compute an intermediate quantity y, and then you compute f. And the way to set this up is you compute the differential. So you have a function, I don't know, g1 and g2. And so the differential of g2 rond, I don't know, composed with g1 applied to x is equal to the differential of g2 at g1 of x composed with the differential of g1 at x. And as I'm sure Eric told you, the gradient is the transpose of the differential, right? If you take the matrix representation of the differential into Jacobian, and the gradient is the transpose of the Jacobian. This means is that if you want to compute the gradient of this guy, if this guy is of dimension n and this guy is of dimension 1, some intermediate quantity of dimension m, then you have to take this and transpose it. And when you transpose it, you switch the order of these things. So you have to start, whenever you compute gradients, you have to start from the ends and make the information flow back to the beginning. Okay. And this is a very general trick. Sorry? Yeah. So this is just to because this is not central to what I'm saying, but this is, so for instance, consider f of x. Okay, let me not call it x. Okay, f of x is equal to C transpose y, where y solves a x y is equal to b, or b y, bx, something like this. Okay, so typically, I don't know, you have a position of the atoms, wave function, energy, right? And the wave function satisfies an equation, which is here linear, with parameters of the equation given by the atomic positions. Okay, what you want to compute is the gradient of f. So the gradient of f how do you compute it? In this case, it's simple because y is a minus 1 bx. So dy over dx is a minus 1 db over dx. And grad f is, so I'm going to say, okay, so just to be, yeah. Okay, so grad f is a minus 1 times a minus transpose times c. Sorry. So actual way to compute this is you take a variation delta x, that gives you a variation delta y, which is given, so that gives you a variation delta b, which is db times delta x, the differential, okay? That gives you a variation dy is equal to a minus 1 times delta b. B is a vector, so this is of size m, this is m times m, and this is of size m.
But it depends on x.
But it depends on x. It's a function b of x. Yeah, it's a function of x. Yes, it's a function of x. Okay. So dy is equal to a minus 1b delta b, and then df is equal to c transpose delta y. Okay. So now, if you want to compute the gradients, you have to express delta f. So again, I'm considering a small increment delta x, and I'm looking at how this small increment propagates to the final results. And now if I want to compute the gradient, what I have to do is I have to go back in the chain, you have to work out the algebra, and you find out an expression for that. The expression doesn't take more time to compute than simple. What? Sorry, define what? Why do I need A? I mean, this is just a simple model of like y being a wave function. So in practice, this is a Hartree-Fock equation, so it's non-linear, but you ask me for a simple model, so I'm taking a simple model. Okay, we can discuss more this if you.
I take it in my matrix instead of A.
If you put the matrix of instead of A, sure. Yes. Yes.
Just to be sure. So the idea is that you want to express just df at the end of the day. It has the scalar product between dx and something.
And the gradient.
And then you pick up the...
Yes. So you write out df. So you take this expression, which is not that complicated, but I'm lazy. So you have df is equal to something transpose delta x, and that's the gradient. And actually, when you look at what the gradient picks up, you find that it goes in reverse. So you have the C here, and then you have something like a dB transpose, and then you have a minus 1 transpose or something like this, or the reverse. A minus transpose here and dB transpose, something like this.
And what is different from just like the stupid chain rule?
Yeah, it is the stupid chain rule. It's just that yes, it's just that if you do this in a systematic way, the result you find is that you can compute this thing in the same time it took to compute the actual problem.
And you don't have essentially have analytical intermediate.
No, I mean, so here you see this was an equation. So it turns out this equation was linear, but if you have a non-linear equation, you can linearize your non-linear equation close to the solution. And then
because you're assuming small variations and so on.
Yeah, you're computing derivatives.
So you are essentially getting directly with the numerical gradients, even though you don't know exactly it's wrong because you have
Yeah, it's just a systematic way of setting up the computation you do by hand. But the main takeaway I want from this is that it's always possible with lots of work to find the gradients in a reasonable time, let's say. Okay, sorry, not coming too far, but it's an important point, and we can discuss more. And if you're interested, I have notes on this on my web page with notation that Nissan likes.
Verify. So you calculate the gradient using an analytical structure of the function, right?
Yeah.
Like essentially you calculate an analytical gradient.
Yes, but this is, I mean, the function doesn't have to be explicit. You see here, y solved an equation. Yeah, yeah.
One object of the calculus, and there appears how to construct implicit function.
Yes.
Right. That's normal.
Yeah, yeah.
I was just thinking that initially you proposed that people usually do this like the finite difference when they don't want to do analytical consideration. Yeah,
but this is a very bad idea for gradients. Because if you do finite differences here, you have to compute n times the function. And what I'm saying is that there's always a better way to do it. Yes, even if your function is super complicated. I mean, this could be you want to compute the derivative of the position of the polarization of a molecule modeled using coupled cluster with respect to atomic positions. You can just work.
Just a question. So in quantum chemistry, for example, we are careful to do the distinction between, for example, if you take the gradient of the ultrafast energy with respect to the molecular concentration, that's something that is quite easy to do because you have an energy that is variational with respect to the coefficient.
Yes.
But now, if you'd like to take the derivative of the MP2 energy with respect to the altitude, this is way less easy because it's not variational. So it really depends on your problem.
No, man, it's not because it's not easy that it's not feasible. It's just harder. But it's just harder in terms of actually doing the work. But in terms of computation time, it's not. It's not fun.
It's more time consuming to compute the MP2 gradient.
Actually, no. I mean,
you need to solve the additional equation to get the rest.
Yes, but if you do things properly, you have to solve one additional equation.
Sure.
So it's twice as costly.
But you don't have to do anything at the artifact level.
Sure.
So you still have to do something.
Yes, but it's if it's 3 times as costly to compute gradient, it's okay.
Okay.
My point is that it's 3 times as costly to compute gradient. It's not 1,000 times if you have 1,000 times.
The cost doesn't
scale with. Yeah, it doesn't scale with it. Okay. If you're interested, there are notes on my webpage. You look adjoint on my webpage. There are notes on this. Anyway, sorry, I did not actually want to talk about this, but it's an interesting point. So okay. So this is the reason why.
You always can obtain the claim was that you can obtain the gradients in the large spaces.
Yeah. Or twice or 3 times, but with using this trick. But okay, this is not a lecture on this trick, so it is interesting. I could talk about this for ages, and I've actually talked to some members of the audience about this for ages. So. But okay, we can talk about this later. So my point is gradients are good, use them, right? Okay. So we're going to be looking at this nice equation. What is this nice equation? I guess you all know the intuition behind this. Somebody has explained it to you already. You're at a point, you look in which direction do I descend the most? So this is the steepest descent direction. You go into that direction. Okay, you're on a mountain, you want to go down, you look, yeah, okay, here, I'm here, where do I have to go? Here, I go there, okay? And you make a small step, okay? So that's gradient descent. This is actually not a good example because it's not curved, but anyway. Very good prop. Thank you to the LDL people. Okay, so what can we say about this? So first, I also want to make a note on the gradients, because apparently quantum physics people like gradients, complex numbers. So what happens? Okay, I'm going to switch notation. Do I want to use energy for the probably? Let's be honest, we all minimize. Yeah, okay. Let's use energies. Doesn't have to be energy. Let's assume energy. So sometimes X is complex. So what happens when you want to do this? It's actually very easy. You just have to pretend that they are not actually complex numbers, and you have to pretend that they are real numbers. So you see this Cn as being R to the 2n. So what it means is that the expansion, what will it look like? It will look like E of X plus real part of this times H. This is the actual definition of the gradient if you have an E from Cn R. This is the definition of the gradient of E. It's defined by this formula. All right. Why does this coincide with the usual definition for real? So if you see Cn as being R2n, just because if you have Z1 is equal to A1 B1, sorry, A1 plus I B1, and Z2 is equal to A2 plus I B2. If you look at the real parts of the complex of the scalar product, so this is the usual scalar product in Cn. So the real part of this turns out to be equal to A1, A2 plus B1, B2. Okay, which is the scalar products of A1, B1, A2, B2. So by taking the real product, the real thing here, it's the same as if I was considering R to N to R functions. All right. So for our purposes, I mean, I don't know how standard that definition is because nobody writes this in books because nobody cares about this in books, just because it's so easy. But just to avoid being confused, this is the definition for complex numbers. This has absolutely nothing to do with the definition of complex derivatives. So if you know that definition, forget it completely. It's not relevant here. The definition of a gradient has nothing to do with holomorphic functions and okay. And in the same way, if you want the second order is going to be the real parts of H times this. So square and cube. The only thing you have to take care about here is that this here is not a n by n complex matrix. Right? This thing here, it's a linear operator from Cn to Cn, is not C-linear. Okay? Meaning that it's not a n by n matrix. It's just a linear, meaning that you have this guy times H1 plus lambda is H2 is equal to whatever it should be, only if lambda is real. Okay. Yes, it is equivalent to doubling the number of variables. The point is if you want to do a Newton method, for instance, on this kind of problems, you cannot do the Newton method by staying in Cn. You have to use the R2N and make a big matrix. Okay?
What do you mean by
Meaning that you define a function, you define no, it's not obvious. It's you have the E of you define E of Y in being E of X on this Y index Y, where so where Y belongs to R to the 2N and X Y is equal to X 1N plus I X N plus 1. Okay. And then this is a R2N to R function, and you just use standard technology. Okay. So for first order, you can stay in complex arithmetic, but for second order, you have to go into real arithmetic. Okay, that being said, I'm going to leave out the complex numbers and just do the real numbers just because it's the same. Okay. So back to gradient descent. What can we say about gradient descent? The gradient descent is like the prototypical optimization method. Understanding it is very, very important for understanding more complicated variants. So if you want to understand conjugate gradient or BFGS or any kind of more complicated method, you have to first understand what's going on here. So the very nice thing about this is that you can compute E of xn plus 1 simply by a Taylor expansion. Okay? What is the Taylor expansion? Well, you just do it. So it's that plus the gradient of E at xn times minus alpha gradient of E at xn plus big O of, let's say, alpha squared D of xn squared. Yes? So this is equal to E of xn minus alpha norm of the gradients xn squared plus big O of alpha squared. Okay, what this means is that the first order variation, so if you think of alpha as being a small parameter now, you see that this has to first go down. So if I look at the energy xn plus 1 as a function of alpha, you know that it does this. Then hopefully, if you're in a region where the function is convex, it does this, and then weird things. Okay. So the important point is that if you take alpha small enough, then the energy will go down. Okay. So if alpha is small enough, at least small enough compared to what? Well, compared to like this number, which depends on the curvature. So the more curved your function, the more stiff your function is, the smaller alpha has to be for this term to beat that term, right? Because the second order term will have a curvature term, and it should be, if your function is very curved, alpha should be very small. All right? So this is very nice mathematically because we like in mathematics, I don't know if you remember, functions that decrease, sequences that decrease are nice, because sequences that decrease and are bounded below, they have no choice but to converge. So if you have a, okay, now I look at E of xn as a function of n. If it goes down, and if it's bounded below, so if it's not bounded below, you have no right to begin with the minimization anyway, so forget about it. But if your function is bounded below, then E of xn has to converge. Okay? And this is very nice because it means that your algorithm cannot do weird things, like it cannot cycle, cannot oscillate between two states or something. So the lesson here is that if alpha is small enough, you get some weak sense of convergence. At least E of xn converges. Then if you are clever and you do math, you can prove that, in fact, the gradient goes to 0. And then if you are more clever and you use much stronger hypotheses like analyticity, and goes to very deep ideas or second order conditions, then you can prove that xn itself actually converges to a local minimum, to a critical point, let's say. Okay? So this is the global convergence analysis of the gradient method. And the thing to remember is that if you take your step size small enough and your function is not too weird, so if the curvature of your function is bounded, so if you look in books, they will use the word Lipschitz, which is a fancy way of saying your curvature has to be bounded. Then you take your alpha small enough, you will converge in some sets. Okay? There are weird examples where the function, there exists a C infinity function where E converges, grad E goes to 0, but xn does not converge. It's a mathematical curiosity. Sorry? It is useful in practice. It's not useful in theory because you have to do more work, but in practice, of course, it is more helpful. But I'm going to discuss this later. In practice, I mean, what I should have said is never do this in practice. Okay? Okay. Everybody does this in practice? No. Don't do this. Use whatever, use a library. Okay, I know you like Fortran, so I'm sorry you cannot use libraries, but use proper language. Julia? Use a more fancy algorithm. So typically use LBFGS. And I'm going to talk about this later. Yes.
If you have a theory that is non-directional and you have no guarantee that the energy is bounded from below, you said that you shouldn't do this, but
if you have this, your iterates, they go away.
People do it.
Yeah, because you hope to be here. If you're here, yes. Yeah, look, the basin of the hypothesis, like the sub-level sets and whatever. Anyway. Okay, so this is the global analysis. It tells you that the thing converges under assumptions. This is not a proper math course, so I'm not going to make the assumptions precise, but there exists a set of assumptions under which the thing converges. Right? Now, a more interesting question from the practical point of view is at what speed does it converge? Okay, because this can converge, but actually be quite slow in many instances, as we will see. Okay, so how do we understand what's going on with this algorithm? If this converges, after some point, you can assume that your function is quadratic. At least you can model your function as quadratic. You have a function that is very weird, but if, okay, so maybe your iterates, they start here, but they are going to asymptotically be here. So here, what you can do is you can ignore the fact that your function is weird, but you can simply model it by a broken chalk by quadratic. Very nice quadratic. Bioquadratic, yes.
Why is that the case? Is this always true? You can have other functions, but if you have x to the power of 9.
Yeah, okay. So of course, I'm going to make this a bit more precise. You can model this bioquadratic if the Hessian is non-degenerate. Okay, so this is the condition I'm going to assume that.
Just by non-degenerate, what do you mean? It doesn't have a zero in it?
Yes, it is a symmetry positive deficit. So assume xn converges to x star, which is some local minimum of the function. Now I compute the Hessian, which I remind you is n by n matrix, symmetric matrix. Oh, of course, what I should have said is that I'm going to assume that in all ways that my functions are smooth. If your functions are not smooth, then you are in for a world of hurt because this is okay. So there are many people working on optimization for non-smooth functions. You have proximal, so you have to use some information. There are techniques, but I'm not going to talk about them. Okay, so I can consider the Hessian, and the Hessian is going to model the curvature of this thing. So I'm going to assume that this thing is symmetric, definite, positive. So what does this mean? I remind you, it means that has positive eigenvalues. Remember, this is a symmetric matrix, so I can just diagonalize it. Okay? Not non-negative, because non-negative, positive, no, non-negative. Yeah, I don't want to be equal to 0. Okay? And under that condition, it is reasonable to assume that your function is approximated by a quadratic. It is reasonable in the sense that what I'm going to say formally by making the approximation to be a quadratic can be proven to work even if you include nonlinear terms. Okay? So now I can make an expansion, a second order expansion of the energy close to x star equal to E of x star. I don't have a first order term. Why don't I? Okay. Why? Ça va? C'est les piles. Allez. No, but I understand that you don't want to record my talk ever. We had the same problem last year. So why is there no first order term? Just because, I mean, this is the point of convergence of the algorithm. And at convergence of the algorithm, if the alpha doesn't go to 0, then the gradient is 0. Okay, so here I just have 1/2 of h, sorry, x, yeah, okay, of x minus x star, the gradient, the Hessian, x minus x star. Okay, so I'm going to assume without loss of generality that x star is equal to 0, and I'm going to call this is equal to a just for simplicity. So now I just have to consider the function E of x is equal to 1/2 x transpose ax.
Okay, so now this is an approximation.
Yes.
So it's,
Yeah. So it's this plus a big O of x star. And I'm just going to drop the third order term. And believe me, the thing I'm going to say work even if you include the third order term. And the proof of this is a Banach fixed point theorem. So if you know Banach fixed point theorem, it's the thing that allows you to convert statement that you make on a linear level to statement on a non-linear level. Local statements on the convergence of these things. Okay about this? So what does this mean? It means that instead of this very complicated function, I just take this function. So this is in 1D. In 2D, how do you represent functions like this on the blackboard or in your mind? Well, you cannot. I don't know how to plot 3D. So I'm going to have to do something else. And the best way to plot this kind of things is by contour lines. Okay. So you plot things like this. Meaning here, this is the E is equal to 1, E is equal to 2, E is equal to 3. Of course, the spacing is wrong, but you understand what I mean. Okay. Why do I draw them like this? Because this is equal to constants is the equation of an ellipse. Okay, remember long time ago, alpha x squared plus beta y squared is equal to 1. This is the equation of an ellipse. Okay, so the isolines, the contour lines of my functions are going to be given by ellipses. Okay, so this is my function locally near x star, which I've set equal to 0. And otherwise, if you go further from x star, the contour line, they start to wobble a bit, and so they do. Okay. But close to x star, they look like ellipses. Okay, and that's nice because on this, I can really understand the convergence of the gradient method. Why? Because what is the gradient of this function? Did Derek do this? Well, you know this, right? The gradient of this function is given by AX. Okay. Basic exercise. If you don't believe me, you just do it by hand. Several ways to do it. It's one way and the wrong way. Anyway, so you compute, you find this AX. Okay. So the gradient method is simply xn plus 1 is equal to xn minus alpha times a xn. Of course, this will converge to 0. This is expected because I've set my origin to be x star. Okay. So this is equal to 1 minus alpha a times xn. By 1, I mean the identity operator, the identity matrix. All right. So of course you can solve this trivially as being this. Sorry. Okay, so what does this do? So A, I remind you, is a symmetric positive definite matrix. So I'm going to diagonalize it. PDP transpose. And D, this is lambda 1 to lambda n. Okay. So now the thing to do is to switch variables to the eigenmodes if you want, or just xn is equal to p times 1 minus alpha d to the n, p transpose. This is because p times p transpose is equal to 1. Okay, so that works. X0. Sorry, again, 0. So it means that if you change coordinates to the eigen coordinates, you find simply a diagonal equation. So here, what does it mean? It means that my ellipse, I shift it back so that the principal axes are the coordinate axes. Okay? So this is very easy to analyze. So for instance, if I define xn, yn to be p transpose xn, I find xn is equal to 1 minus alpha d to the n y0. Okay? Yn is what? Is simply the coordinates of xn in the eigenbasis. Okay? Okay, so yn I is equal to 1 minus alpha lambda I to the n y0 I is simply the i's component of y. Okay, why is this nice? Because this is trivial to analyze now, because you have simply mu to the n. Mu is real. Mu is 1 minus alpha I, lambda I. What is the behavior of mu to the n? Or if mu, so okay, I plot mu to the n as a function of n. If mu is bigger than 1, you go like this, you diverge. If, so that's one type of behavior. So this is, okay. Mu bigger than 1. This, 0, mu, 1, this will implode.
What is mu?
Mu is any number. So right now I'm just looking at mu to the n for mu any number. And I'm going to apply this later to mu is equal to 1 minus alpha. Okay, so this is monotone implosion. So monotone explosion, monotone implosion. This is oscillatory implosion, right? So I don't have 4 colors anyway, so it does something like this. Okay. Oscillatory implosion, and mu smaller than -1 is oscillatory explosion. So you do this, but you overshoot and you explode. Okay, so these two are bad. What we want is this, because remember, we want to converge to 0, to x star. Okay, so the condition we have now this these are nice strokes, but take a lot of. So to get convergence, I have to have mu I smaller than 1. Okay. If you want to do fancy math, this goes into the map from xn to x plus 1 has to be a contraction, and this in turns is the same as this. Okay. Well, except there are always edge cases and so on, but I'm not going to consider edge cases. All right. So mu I remind you, was 1 minus alpha lambda I. So what this tells you is that alpha has to be smaller than 2 over lambda n if lambda n is biggest. Okay, this is a stability condition for the gradient descent. If this condition holds, then gradient descent will converge. Okay, remember what I told you before. If your function is very curved, you have to have a small step size. So here, this is the curvature of the function. If your function is very curved, you have to have a small size. Yes? Yes, in this case, this is called preconditioning, essentially. I'm going to talk about this later. No, this is for the theory. Sorry? Yeah, but this is for the theory analysis. In practice, this is not how you do it. In practice, you use, as you said before, you use line searches. So to guarantee that the energy goes down, you don't have to compute the full Hessian to get the curvature and take a small thing. You just have to make sure that the energy actually goes down when you compute it. So this is much easier. But this is important for the analysis and for intuitive understanding of what's going on and quantitative understanding. Everybody agrees with this? Okay. Now, so again, this is intuitive, right? It says that if this is the E of alpha of exn plus 1 as a function of alpha, then you should take alpha to be in this zone and not in that zone. Okay. Now, more interesting, what is the speed of convergence? What is the speed of convergence of this? Well, you get norm of x goes asymptotically. Oh, okay. So remember, we have this. So whenever you have a vector with multiple components and each one decays at a specific rate, exponential rate. So what this means is that you will have multiple components and they will go to 0 at different speeds. Some will go fast, maybe some will oscillate. Some will go fast, some will go slow. The asymptotically, what's going to matter for the convergence of the whole vector is the slowest of this. Okay, so the convergence goes, I'm going to be imprecise here, but it's not the first time, so it's okay. The convergence goes as max over I of 1 minus alpha lambda I to the n. All right? Asymptotically, this is what you will see on your computer if you plot the norm of the gradient as a function of the iterations. This is again all for a fixed step size, huh? Taking alpha constants. Okay, so what is the max of this? Well, 0 here, 1 here, minus 1 here, and the eigenvalues, the mu i's, they will be here, somewhere here. What is the maximum of this? It's the maximum of this one and of this one. Okay, unless you get unlucky, but essentially it's this. So now you can try to ask the question, what is the alpha that minimizes this quantity? Okay, what is the alpha that minimizes this quantity? You have two situations. Remember the mu I, the eigenvalue of the iteration matrix, the thing that will determine the convergence. So the mu i's are 1 minus alpha lambda I. Okay. So if you are in this situation, what does it mean? Is this a good alpha? I can do better. Sorry, this is minus 1, this is 1, 0 is here. The 0 actually doesn't matter. No, because you see, we want to the max of this. Doesn't care if it's 0. The max of this is the max of this and of this. Don't really care about the. No, sorry. Yes, yeah. Wow. Okay. You don't care about this. So this is a. Yeah, so this is a bad situation. What you should do is you should increase alpha, right? Because if you increase alpha, you dilate your spectrum like this, and therefore you will reduce this guy. So this is the situation of underdamping. You have been too cautious with your alpha. You have to take an alpha small enough, so too small. It means that you will the dominant mode will be underdamped. Sorry, overdamped. Okay, you dampen too much. Your alpha is too small. This is a bad situation. So this is overdamping. The other situation is you have a spectrum like this. So you still get convergent, but this is again bad because you should reduce your alpha, right? If you reduce your alpha, you contract it here, And this is under damping. So the best point, the point that minimizes the convergence rate, that optimizes the convergence. So optimum when this guy in absolute value is equal to this guy in absolute value. Okay, so if you want, nu1 is equal to nu n, which is 1 minus alpha lambda 1 is equal to the opposite sign, so minus 1 minus alpha.
When you say over damping,
Yeah.
If alpha is equal to 0,
then it's very, very, very damped because you do not move. If alpha is equal to 0, everybody is here.
yes,
This is very overdamped.
it's over damped.
Yes. On your saying, overdamping is when you go very cautiously here, and sorry, overdamping, and underdamping is when you go oscillatory. Sorry, this is bad. When you are oscillatory and too oscillatory. Okay. Okay, so here you compute a bit and you say that alpha is equal to 2 over lambda 1 plus lambda n. Okay. So it's 1 over the average between the biggest and the lowest eigenvalue. Yes.
Just a remark, when you are trying to check how much converged you are, the oscillatory case isn't problematic, and in this case, you would want to have the non-oscillatory case.
Why would oscillatory be bad?
Because I guess I would check if the norm of the distance between two consecutive points is
but-
decreasing, for example.
Yeah, but the distance, you will not see because the distance is this quantity, right? The distance is always positive, so you never see when you plot convergence rates, convergence curves, it's very hard to distinguish between.
No,
You
you take x n plus 1 minus x n, you take the norm, and if
Yes.
this goes to 0, you're converging.
Yes.
If you are oscillating, this would be artificially larger, right? No? I
Why?
don't know.
If you want to extrapolate the convergence from xn plus 1 minus xn? Yeah, I guess this would be
In
bad.
this case, you would like to maybe shift a little bit.
Yeah, but I mean, don't extrapolate and you're fine.
Well, it's oscillator, you have this downward. It's also that bad. Well, if you put your-
Yeah. Oscillatory. Yeah. I don't.
So if your lambda are really symmetric with respect to 0, you will have lambda 1 equals minus lambda n.
No. So the lambdas are always positive. Remember the lambdas, they are the eigenvalues of the matrix. This is the muse. I don't know, my notation may be bad, but I don't have a better one. Okay, so this is the best fixed alpha, let's say.
So the inverse of alpha is a curvature.
Sort of.
So you're saying
It's homogeneous to curvature.
that the optimal value is just the average of the two
Yes.
curvature. in the two
Yes. So if you have an ellipse like this, the optimal value that you should take to get the closer to convergence should be 1 over the average. Okay, so now the convergence goes like so you can compute either from this or from this because they are the same. So 1 minus 2 over lambda 1 plus lambda n times lambda 1 to the n. And now you do a bit of algebra and you find that this is equal to kappa plus 1 over kappa minus 1 to the n, where kappa is the condition number of A. Okay, so this, no, kappa minus 1, or kappa plus 1, hopefully. Okay, so remember, so this guy is always bigger than 1. So the bigger kappa is, the closer this guy is to 1, and the worse the convergence is, because 1 to the n doesn't converge to very far. 0 to 999 to the n doesn't converge very quickly. If on the other hand, kappa is relatively small, it's always bigger than 1, but maybe it's 4 or something, then you get very quick convergence. Okay, so geometrically, what does this tell you? It tells you that the more eccentric your ellipses are, so the more badly shaped, the further they are from a circle, the worse the convergence rate will be. And it's not very hard to understand why, because if you are here, you have to go in the gradient direction. Of course, you should not go into the gradient direction to get the best result, but this is what you have to do. And you have no other choice if you're doing the gradient method. So you go in this direction. Where do you stop? Well, you have to stop relatively quickly because the function is very curved in that direction. Okay, so you have to stop relatively early here, and then you do another step. So you go here, here, and you go here. Yes. So the problem is that it's like a stiff ODE solver. If you know this, you have to take small steps because you want to avoid going too far in this direction. But because you're taking two small steps here in that direction, you're taking a small step in that direction, and then that leads to slow convergence. This is a zigzag phenomenon.
Lambda n is equal to lambda 1, so in the case of
so this is the circle. In the case of the circle, the gradient points straight to the center.
k is equal to 1, and then you have 0, and then it converges.
Yes, because if you adjust your step quickly, you have just one eigenvalue here. Right? So if you adjust the alpha in a proper way, meaning if you stop precisely here, then you're good. Okay, so this analysis is for fixed alpha. If you take optimal alpha, it's harder to analyze, but you hope that the conclusion of this carry forth to the case of the adaptive. So the lesson here is the more badly conditioned your problem is, the bigger this guy is, the slower is the convergence of the gradient method. Which is, in some sense, reassuring, because this is nature telling you if you have trouble converging your problem, maybe your problem is bad to begin with, right? Because this number is connected to a lot of things like sensitivity to noise or sensitivity to nonlinear effects or sensitivity to, okay? If your problem is badly conditioned, you're going to have trouble solving it. And if you try to solve it and it's very, very, very slow, maybe it's a sign that you studied it up wrong. Or that you're just doing bad things, maybe. Is everything clear on this picture and on this local analysis?
So now, Eric told us that the gradient depends on the inner product.
You're
So
spoiling
it's
the,
going to,
yes.
show how
Yes.
you can use that.
Yes. And this is called preconditioning, in fact. And it's related to Andra's question from earlier. So, of course, we understand now what's going wrong. Is that we do not want to go in that direction. The gradient is not a good direction. The gradient is only going to oscillate. I want to go in that direction. So in some sense, I want to take a step in that direction, an alpha in that direction, which is different from the alpha I take in that direction. And this is in fact what exactly Newton method is doing, right? Because if you look at normally Newton method, so if I take, I don't know, I fix this equal to lambda 1, lambda 2, then what is it doing? It's doing okay, xn plus 1. So if you tuck, so this is xn plus 1 is equal to xn 1. So this is for simplicity. Huh? Xn 1 minus 1 over lambda 1 times the gradient, but the gradient is what? Is lambda is 1 times xn 1. And then it converges in one shot. Okay. So the gradient method is the Newton method is exactly implementing what Andreas said, that alpha should be a vector. But alpha should be a vector in the eigenbasis. Okay. Here that works because the Hessian is diagonal. If the Hessian is not diagonal, it should switch to the eigenbasis, do the inverse on the diagonal, and switch back to the real basis. So this is exactly what this is doing. Okay, so these ideas are very intimately related. Okay, so what is the issue here? The issue is that the gradient, this is equal to AX, in our case. This is the residual of our equation. This is the thing we can compute. The thing we would want to compute is the x minus x star, which of course in my notation is the same thing as x, and this is the error. This is the thing we can compute. This is the thing we would like to compute. Because of course, if you can compute this guy, you can get back to x star in the quadratic approximation. Okay. So the whole trouble with our badly conditioned example here is that the residual, just do this drawing more properly. The residual is this guy. This is AX. This is very different from the error. Sorry, this is not obvious because I'm very bad at drawing, but the I don't know. The residual will be something like this, and the error will actually be something like this. Okay, because it's this. So this is minus x. Yeah. So the problem is that the residual is a very bad proxy for the error. The whole thing of the gradient method is that I'm using the gradient, AX, as a proxy for the error. I would like to go in the direction of the error. I cannot go in the direction of the error, but I can go in the direction of the residual. So I'm going into the direction of the residual. If your problem is well conditioned, X and AX are not too far from each other. They depend by scaling essentially, but the scaling I can absorb with the alpha, so it's fine. If your problem is badly conditioned, it means that the residual has nothing to do with the error. Okay, so in other words, if your error, I think that this I saw this in a physics paper and I like this picture, so I'm taking it. So this is x1 and x2, so I'm going to put them. Okay. If you have a well-conditioned, this is in 2D, huh? If you have a well-conditioned problem, then you will have arrows that are not too different. If you have, so this is well conditioned. If you have if you have a badly conditioned problem, one component is going to be disproportionately bigger than the other. And this is what screws up your convergence. What you should do is you should put it back by some kind of Newton method.
You have to turn the whole thing and divide by
Yeah.
the non-hypothesis.
Yes. So this is exactly what Newton is doing. Problem is that Newton is super expensive. So is there a way to still do a good thing without doing the Newton? Yes, and it's called preconditioning. Preconditioning is the idea that I might not know how to make the residual exactly equal to 0 in the quadratic approximation, but I might know how to make it less bad. Okay, so typically, this is the situation where you know. Okay, I'm going to take something that chemists like. It's the full CI Hamiltonian, Davidson. Okay, if you know Davidson. Davidson, you deal with a matrix that has a big diagonal. I don't know, 20, 400, something like this, 800. Because the higher you go in the excitations, hopefully the thing, okay. And then you have relatively small, so this is the Hessian. Okay, strong diagonal dominance plus relatively small Euro perturbation. So on this system, it's reasonable to assume that the diagonal is a reasonable approximation to the Hessian, and then to use this in order to correct the relationship between the residual and the error. Okay, and this is called preconditioning. Another way to see preconditioning is that, again, with the ellipses, this ellipse looks quite bad. It looks quite flattened. But if you change goggles, if you change glasses and you change glasses into a direction with where the axes are stretched, then hopefully this becomes maybe not quite round, but at least more roundish. Okay, and then you will get better convergence. And again, this is very related to what Eric said. The gradient depends on the metric. There's nothing absolute about the gradient. Here, the gradient was quite bad, but here, the gradient, if you just change your axis, if you change your metric, the gradient can become quite good. Okay, this is why preconditioning is useful. Yes.
So when on earth we think the alpha has to be a vector,
Yes.
to have alpha be a constant and changing the gradient.
So I mean, what should actually happen is that alpha should be a matrix. It should be the inverse Hessian, and then you're good. So in practice, you do whatever you can. Okay. Good. Blah, blah, blah. Okay, so gradient method we said is bad when your problem is badly converged. Use preconditioning if you can. Of course, it's always a trade-off because a Newton method is too expensive. So if you have some intuition into your problem, you can use that to get preconditioning. So that's one way to improve the convergence of the gradient method. Another way, which requires no intervention from your part, just a switch in your favorite optimization library, is to use a better algorithm than this. So in the linear regime, this is called Krylov methods. And in the optimization world, this is called quasi-Newton. So quasi-Newton is the idea that you don't have to be passive during the optimization, right? If you're doing this zigzag thing, you can figure out that you are in a zigzagging pattern and you can try to correct for it. Okay? The way to do this is by approximating the Hessian. So we've seen that Newton method was very good. It converged in one step for a quadratic model. So you try to learn. And the way you try to learn is that during the iterations, you're going to observe xn, and you're going to observe gradient of xn. Okay, for a bunch of realizations of this xn and grad of x e of xn. And based on this, you can sort of try to impose consistency information on your hash chain, because you know that, for instance, the gradient, if E is quadratic, then the gradient minus the gradient, for instance, is equal to the Hessian. I'm not specifying where the Hessian is taken because I'm assuming the function to be quadratic, times xn minus 1. Okay, so you can try to construct a matrix that satisfies this condition. Okay, so during the iteration, you build up information on your on the geometry of your problem, and you find a matrix that will satisfy this. There are many, many variants of this idea, but the best one that people use in practice is called LBFGS. Limited memory, Broyden, Fletcher, Goldfarb, Shannon. Okay. Okay. So it's basically a version of this. So what this does, it stores like 10 iterations in memory, and on this 10 iterations, it tries to impose constraint. There are many subtleties, but they are not super important. So I'm going to skip this. Yeah, so you approximate the inverse. You do not store this matrix explicitly. You just store the matrix low rank. So of course, there are infinitely many matrices that satisfy this, right? But if you restrict your matrix to be of the form 1 plus U transpose, there's only one matrix which is of this form and satisfies this. So now if you have 10 iterations, you do this with a rank 10 matrix. Okay, I'm not going to bore you with the details because this is kind of a black box that you can just use, and in practice it speeds up the conversions. So typically, if you code up a gradient method and you look at the log of xn minus x1 minus 1, if you find that your method, the thing is very, very flat, is very, very linear, it means that you get exponential convergence. And this is exactly the regime in which this approximation, it means that you're in a quadratic approximation. And then this technique is very efficient. It maybe will not help you too much here, but so this, if your gradient descent looks like this, function of n, then your BFGS will look like this. It will be much faster to converge. If your gradient descent curve looks like crap, then BFGS will look like. Okay. Oh, and another thing I forgot is so the only thing I've not said is how do you pick alpha, the line search parameter, the step size parameter. Well, there are plenty of schemes like the Army-Zero scheme or things like this. But in practice, you pick a step. If your step is too big, then you find that your energy is too big. You reduce, and then you do fancy techniques. Okay. So an optimization is three things. It's an update rule plus a metric plus a line search. Let's see, modern optimization. So typically this is a steepest descent or LBFGS. This is preconditioning. And this is whatever's in your software package. If you combine those three ingredients, you have a robust and efficient optimization, first order optimization. Okay. There are more things you can do. There are trust region, there are other techniques, but I'm not going to talk about this. Okay. If you forget about this, then you have to hand tune your your alpha parameter. And that is very annoying and it's suboptimal. If you don't do preconditioning and if your problem is badly behaved, you are susceptible to slow convergence. And if you forget about this and just do steep at distance, you are leaving some efficiency, some free efficiency on the table. Because BFGS is not more expensive, not very much more expensive. Yes.
About the line search, can you give few words?
Okay, so typically, so what do you want your alpha to look like? Okay. You do not want it to be too small because if it is too small, then clearly you should take a bigger one and you're in the overdam situation. But you also want to guarantee that the energy goes down at each step, more or less. Because otherwise you have no hope of getting global convergence. So typically a good algorithm is you start with a parameter. You find out if it's too small because you can compute. So there's an Armiro rule, but okay, let's forget about this. You can figure out that this is too small, or even blindly you just increase it the next time. Okay. And then if it's of course, if it's here, you reject, and you take you try this, and then you have some criterion that tells you, okay, this is relatively good, this is relatively good, and you sort of try to blindly approximate. Or you can do fancier thing, like you can take 3 points, do a quadratic extrapolation, and do things like this. But it's like a compromise, right? Because you
You only do several evaluations and
yes.
take the best, and based on that you change.
Yes. So usually, I mean, the packages differ, but so typically you do either one and you're good, or you do 2 or 3 and then you find an extrapolation and you are more precise, but it takes more time. Compromise.
And the trust radius is a type of line search.
Yeah, you can see it like this. It's a way of globalizing the unity set. Yes.
What do you think about the conjugate gradient?
So conjugate gradient, I put it in these directions. Yeah, it's a way of okay, there are 2 carriers too far, but it's building on the same kind of intuition like this. It's building on the same kind of quadratic approximation, just using a different rule to update. I would say CG is more efficient in terms of storage, but it's less efficient than LBFGS. So more susceptible to good line searches. To get good CG, you need a good line search. Yes. Yes.
The best circles and the tallness, it's related to the metric.
Yes.
So my question is it an optimal, how many metrics do you have?
You can choose. So okay. So by change of metric, I mean the following. I was not insisting too much on this because I think Eric told you about this, but you choose this is equal to this, right? This is your choice. And if you do the gradient descent with the gradient induced by this metric, then you find xn plus 1 is equal to xn minus, is it s or s minus? I never remember. S minus 1. Where this is the flat gradients. Meaning the gradient with respect to the inner product. Yes. Yes, the best metric is the one for which S is equal to liberation. Because then it's just Newton. So this is a very interesting observation, is that the Newton, you can interpret Newton as a change of metric, where you instead of doing this, you map it to this. Okay. What should we have? 3 minutes? Good. Actually, I think this is a good place to stop. So and also we already. So maybe I stop here unless there are questions. Hmm.